in the spaces between stars. Where darkness stretches for light years in every direction, something remarkable unfolds with the patience of geological time. Here, in the interstellar medium, molecules that will one day become the building blocks of life drift through regions so vast that Earth's entire orbit would appear as a single point of light. The temperature hovers just a few degrees above absolute zero. Yet even in this cosmic winter, chemistry continues its quiet work. Hydrogen atoms, the universe's most abundant element, encounter carbon drifting from the dying breath of ancient stars. They meet in the shelter of dust grains, tiny specks of silicate and ice that serve as laboratories for organic synthesis. On these microscopic surfaces, amino acids begin their slow assembly, one molecular bond at a time. Glycine forms first, the simplest of the 20 amino acids Earth's proteins require, then alanine, serine, and others follow, their structures emerging from the fundamental forces that govern matter itself. These stellar nurseries, regions where new stars will eventually ignite, become inadvertent factories for biological precursors. The Orion Nebula, visible to the naked eye as a fuzzy patch in the winter constellation, harbours clouds of formaldehyde, methanol, and formic acid. Radio telescopes detect their spectral signatures across hundreds of light years, chemical fingerprints broadcasting the presence of organic complexity in the cosmic dark. Scientists have identified over 200 different molecules in interstellar space, many of them familiar from earthly biochemistry. The irony settles softly. The same processes that create stars also create the molecular foundations for life. Yet these twin creations may never meet for billions of years. A single dust grain, no larger than a virus, carries its cargo of organic molecules through the galaxy at speeds that would cross Earth's diameter in just a few hours, yet takes millions of years to travel from one star system to another. Time moves differently in the cosmos, where patience is measured not in seasons but in the slow rotation of spiral arms. Within these molecular clouds, density varies like weather patterns on a planetary scale. Some regions condense into dark nebulae, so thick with dust that they block the light of stars beyond. Others remain tenuous. Their matter spreads so thinly that a cubic meter might contain fewer atoms than a single breath of Earth's atmosphere. Yet even in these sparse regions, the chemistry of life proceeds with quiet persistence. Water ice accumulates on dust grains, creating tiny frozen worlds where more complex reactions can occur. Ultraviolet radiation from distant stars provides the energy needed to break and reform chemical bonds, while cosmic rays, high-energy particles accelerated by supernovas and black holes, add their own catalytic influence. The result is a slow but steady production of organic molecules, accumulating over millions of years like sediment in a cosmic riverbed. The mystery deepens when astronomers consider the sheer abundance of these materials. Every cubic centimetre of interstellar space contains, on average, about one dust grain. Multiply this across the volume of our galaxy, and the total mass of organic-rich dust exceeds the mass of millions of Earths. The Milky Way becomes not just a stellar city, but a vast library of biological potential, its pages written in the language of carbon chemistry and scattered across the emptiness between worlds. Some scientists propose that this interstellar organic synthesis represents the universe's first attempt at biology, a preliminary sketch drawn in molecular ink across the canvas of space. Others suggest that these are merely the raw materials, waiting for the warmth and complexity of planetary environments to kindle into true life. The question remains open, drifting through scientific literature like the molecules themselves drift through space. Recent observations have revealed organic molecules in the most unlikely places. the atmosphere of Titan, the surface of comet nuclei, even in the outer reaches of our solar system where sunlight barely provides more warmth than the cosmic microwave background. Each discovery suggests that the chemistry of life is not an anomaly confined to Earth's surface, but a fundamental property of matter itself, expressing itself wherever conditions allow. The process requires no intelligence, no guiding hand, only the basic laws of physics and chemistry operating across spans of time that dwarf human history. A carbon atom expelled from a dying star 10 billion years ago might today be part of a protein in a living cell, having spent eons drifting through space, condensing into dust, incorporating into asteroids, and finally arriving at a world where liquid water and suitable temperatures allow biology to flourish. This cosmic recycling operates on scales both intimate and vast. The calcium in human bones was forged in stellar cores and distributed through space by supernovas. The oxygen in every breath once floated freely in interstellar clouds. The iron in blood cells carries the signature of stellar nuclear synthesis, making every living thing a temporary gathering of elements, borrowed from the cosmic inventory and destined to return to it. As these organic rich dust grains drift through space, they sometimes encounter the gravitational influence of forming solar systems. Young stars, surrounded by disks of material that will eventually coalesce into planets, sweep up whatever crosses their path. The organic molecules that formed in the cold depths of space suddenly find themselves in warmer, more dynamic environments where they can participate in increasingly complex reactions. The chemistry of deep space unfolds with a precision that would challenge the most sophisticated earthly laboratories, yet it operates without test tubes, without controlled temperatures, without the careful measurements that human science requires. In the Horsehead Nebula, 400 light-years from Earth, carbon monoxide molecules collide with hydrogen atoms in a dance choreographed by quantum mechanics. The temperature here measures 15 degrees above absolute zero, cold enough to freeze air itself into crystals, yet warm enough for chemical reactions to proceed at their own unhurried pace. Each collision between molecules carries the potential for transformation. A carbon atom, liberated from the core of a star that died before Earth formed, encounters a chain of hydrogen atoms arranged in the precise geometry that will become methane. The reaction requires no catalyst beyond the fundamental forces that bind matter together. No external energy source except the faint ultraviolet glow of distant stars. Yet from these simple encounters, complexity emerges with the inevitability of gravity itself. Astronomers mapping these stellar nurseries discover molecular signatures that read like inventory lists from organic chemistry textbooks. Acetylene, the same compound that burns in welding torches, drifts through space in concentrations dense enough to fuel industrial applications, if anyone could harvest it. Ethanol, familiar from earthly fermentation, condenses on ice grains in quantities that would fill terrestrial oceans. The irony settles gently. The universe produces alcohol on scales that dwarf human civilization, yet stores it in regions so cold and sparse that it would take millions of years to collect a single drop. These reactions proceed without the liquid solvents that earthly chemistry requires. Instead, the surfaces of dust grains serve as meeting places where reactant molecules can encounter each other and form new bonds. A single grain, smaller than a bacterium, might host thousands of simultaneous reactions across its crystalline surface. Silicon and magnesium provide the structural framework, while water ice creates a thin coating that allows more complex organic synthesis. The grain becomes a microscopic world, its geography defined by chemical gradients and its weather determined by the radiation environment of interstellar space. The Eagle Nebula, where iconic pillars of gas and dust stretch across light years of space, demonstrates this chemistry on visible scales. Within those towering columns, dense enough to block the light of stars beyond. Amino acids assemble with the patience of geological processes. Glycine forms first, its simple structure requiring only a few molecular building blocks. Then more complex amino acids follow: alanine, valine, leucine, each one adding to the inventory of biological precursors drifting through the cosmic dark. Scientists studying meteorite samples have confirmed that these spaceborne amino acids actually reach planetary surfaces. The Murchison meteorite, which fell in Australia in 1969, contains over 90 different amino acids, including many that earthly life never uses. This excess diversity suggests that interstellar chemistry explores possibilities that biology later discards, creating a vast library of molecular experiments from which life selects only the most useful variations. The universe appears to be testing chemical combinations long before planets exist to make use of them. The process operates with a thoroughness that human laboratories cannot match. Every possible combination of carbon, hydrogen, oxygen, and nitrogen encounters opportunities for synthesis across billions of cubic light-years of space. Some reactions produce dead ends, molecules too unstable to persist in the radiation environment of interstellar space. Others create compounds so robust that they survive for millions of years, accumulating in dense molecular clouds like sediment in cosmic rivers. Radio telescopes detect these molecular signatures by analyzing the specific frequencies of radiation they absorb and emit. Each compound has its own spectral fingerprint, as distinctive as a human voice. Formaldehyde resonates at specific radio frequencies, creating absorption lines that astronomers can detect across thousands of light years. Water masers amplify radio signals like cosmic lighthouses, their emissions revealing the presence of water vapor in regions where the temperature would instantly freeze any liquid. The mystery deepens when scientists consider the selectivity of these processes. Not all molecules form with equal ease in the interstellar environment. The same physical laws that govern chemistry in earthly laboratories also operate in space. But the conditions favor certain pathways over others. Left-handed and right-handed versions of the same molecule, chemically identical but mirror images of each other, sometimes show preferences that mirror the asymmetries found in terrestrial biology. This molecular handedness, or chirality, represents one of the deepest puzzles in astrobiology. Earthly life shows a strong preference for left-handed amino acids and right-handed sugars, a bias so universal that it suggests a fundamental constraint rather than random chance. Some meteorite samples show similar preferences, hinting that the asymmetries of terrestrial biology might reflect properties of interstellar chemistry rather than evolutionary accidents that occurred after life began. The Rosetta spacecraft, which accompanied Comet 67P for over 2 years, detected amino acids and other organic compounds in the comet's nucleus. These molecules had survived unchanged since the solar system's formation, preserved in the deep freeze of the outer solar system for 4.5 billion years. Their presence confirms that the organic chemistry of interstellar space successfully seeds new planetary systems with the raw materials for biology, delivered by objects that spend most of their time in the coldest, most isolated regions of space. Temperature gradients within molecular clouds create different chemical environments separated by distances measured in astronomical units. Near the edges, where stellar radiation penetrates the dust, temperatures might reach 50 degrees above absolute zero, warm enough for more complex reactions involving larger organic molecules. Deeper within the cloud, where dust blocks nearly all external radiation, Temperatures approach the cosmic background temperature of 3 degrees Kelvin, cold enough to freeze virtually everything except hydrogen and helium. These temperature variations allow different types of chemistry to proceed simultaneously within the same nebula complex. Simple molecules form in the coldest regions, while more elaborate organic synthesis occurs in slightly warmer zones. The result is a stratified chemical ecology, with different molecular species occupying different environmental niches within the same interstellar cloud. The parallels to terrestrial ecosystems remain striking, even in the emptiness of space. Chemistry organizes itself into communities of interacting compounds. Stellar winds from nearby stars occasionally disturb these quiet chemical factories, accelerating dust grains to velocities that carry them out of their birth nebulae and into the general interstellar medium. These grain populations become seeds that can trigger star formation in distant molecular clouds, carrying their cargo of organic molecules across hundreds of light years and millions of years. The galaxy thus maintains a circulation system for both matter and information, distributing the products of stellar nucleosynthesis and interstellar chemistry throughout its spiral arms. The timescales involve challenge human intuition about chemical processes. On Earth, organic synthesis typically occurs over seconds, minutes, or hours in interstellar space. The same reactions might require thousands of years to proceed to completion, yet this temporal dimension adds robustness to the process, allowing even rare molecular encounters to accumulate significant products over geological time. The universe operates its chemistry with patience that compensates for the low densities and extreme temperatures of the interstellar environment. In the silent museums that drift through Earth's atmosphere, stories written in stone preserve the chemical signatures of worlds that formed before life began. These carbonaceous chondrites, meteorites that originated in the asteroid belt between Mars and Jupiter, carry within their crystalline matrices the organic inventory of the early solar system. When they fall to Earth as streaks of light across the night sky, they bring with them libraries of molecular information that have remained unchanged for 4.5 billion years. The Allende meteorite, which scattered across the Chihuahuan Desert in 1969, contains amino acids, nucleotide bases, and complex hydrocarbons embedded in a matrix of olivine and pyroxene crystals. These organic compounds show isotopic signatures that distinguish them clearly from terrestrial contamination. Their carbon bears the nuclear fingerprints of stellar nucleosynthesis, ratios of carbon-12 to carbon-13 that could only have formed in the nuclear furnaces of ancient stars and survived the violent processes that created the solar system. Each chondrite represents a snapshot of conditions in the solar nebula, the rotating disk of gas and dust from which the planets condensed. The organic molecules they contain formed through the same interstellar processes that continue today in distant molecular clouds, then became incorporated into the solid materials that built asteroids and eventually planets. These meteorites thus serve as time capsules, preserving the chemical state of space before Earth's oceans existed, or its atmosphere contained free oxygen. The Murray meteorite, another carbonaceous chondrite, contains over 70 different amino acids, far more than the 20 that terrestrial biology employs. This molecular diversity suggests that the processes forming organic compounds in space explore chemical possibilities more thoroughly than the selective pressures that shaped earthly life. The universe appears to conduct vast chemical experiments, synthesizing every stable organic compound that physical laws allow, then delivering samples to planetary surfaces where biology can select from this cosmic inventory. Scientists analyzing these meteoritic organics have discovered something remarkable about their distribution within the stones themselves. The amino acids are not randomly scattered throughout the meteorite matrix, but concentrate in specific mineral phases, particularly within clay-like materials that formed through the interaction of liquid water with the original asteroid. This suggests that even before reaching Earth, these organic compounds underwent processing in aqueous environments, experiencing the kind of chemical evolution that might represent the earliest steps toward biology. The isotopic compositions of meteoritic organic compounds reveal their cosmic pedigree with unmistakable clarity. Deuterium, the heavy isotope of hydrogen, appears in concentrations 10 to 20 times higher than those found in terrestrial materials. This deuterium enrichment could only have occurred in the extreme cold of interstellar space, where chemical reactions favour the incorporation of heavy isotopes over their lighter counterparts. Each meteorite thus carries isotopic fingerprints that trace directly back to the molecular clouds where its organic components first formed. The Murchison meteorite, perhaps the most studied carbonaceous chondrite, contains compounds that blur the boundary between geochemistry and biochemistry, purines and pyrimidines. The molecular bases that form the rungs of DNA's ladder appear alongside amino acids and fatty acids in concentrations high enough to suggest efficient synthetic pathways rather than random molecular assembly. The meteorite's organic inventory reads like a shopping list for the origin of life, containing virtually every category of compound that terrestrial biology requires. These cosmic care packages arrive at Earth with a gentleness that seems almost intentional. Most meteorites enter the atmosphere at velocities between 11 and 70 kilometers per second, fast enough to create the brilliant fireballs that announce their arrival. Yet the outer layers that experience this heating serve as ablative shields, protecting interior materials from temperatures that would destroy organic compounds. The meteorite's core often remains cold enough to preserve even the most delicate molecular structures throughout its fiery descent. The irony settles softly. These ancient stones, older than any rock on Earth's surface, contain organic compounds more diverse than those found in many terrestrial environments. They represent a kind of cosmic biodiversity that existed before biology itself, a molecular ecosystem that developed in the sterile conditions of space and survived unchanged for billions of years. Earth's early bombardment by such objects would have delivered not just water and atmospheric gases, but also the complete chemical toolkit needed for life's emergence. Laboratory simulations of early impact conditions suggest that meteorite organics could survive the violence of planetary bombardment more readily than previously thought. When researchers fire projectiles containing amino acids at targets simulating Earth's early surface, they find that significant fractions of the organic compounds survive intact, protected by shock-absorbing mineral matrices and the brief duration of impact heating. The same processes that seem most likely to destroy biological precursors might actually have been efficient at delivering them to planetary surfaces. The timing of these deliveries coincides remarkably with the window when life appears to have emerged on Earth, the late heavy bombardment, which occurred approximately 4 billion years ago, would have delivered carbonaceous meteorites to Earth's surface at rates millions of times higher than today. This cosmic mail delivery system operated most intensively during precisely the epoch when chemical evolution was transitioning toward biology, providing a steady supply of organic raw materials to fuel the processes that eventually led to living systems. Recent analysis of meteorite organics using increasingly sophisticated techniques reveals structural details that were invisible to earlier generations of instruments. Aromatic hydrocarbons form complex networks within the meteorite matrix, creating three-dimensional scaffolds that might have served as templates for more complex molecular assembly. These structures show organization patterns that resemble, in simplified form, the hierarchical arrangements found in biological systems. suggesting that the transition from geochemistry to biochemistry might involve fewer discrete steps than previously imagined. The distribution of meteorite falls across Earth's surface provides a global perspective on this cosmic seeding process. Antarctica, where meteorites accumulate on ice sheets and remain preserved for thousands of years, has yielded over 60,000 specimens, many of them carbonaceous chondrites rich in organic compounds. This Antarctic collection represents the most comprehensive survey of extraterrestrial organic chemistry available. A library of cosmic molecular diversity that continues to yield new insights into the chemical processes operating in space. Some meteorites show evidence of aqueous alteration that occurred within their parent asteroids, where liquid water interacted with organic compounds for millions of years before the asteroids were disrupted by collisions. These altered meteorites contain different organic inventories than their unaltered counterparts, with higher concentrations of certain amino acids and evidence for more complex molecular processing. They suggest that the transition from interstellar chemistry to biology might begin not on planetary surfaces, but within the small worlds that drift through the outer regions of planetary systems. The mystery deepens when scientists consider the selectivity of the delivery process. Not all organic compounds survive equally well in meteorites, and not all meteorite types deliver the same molecular cargo. Carbonaceous chondrites strongly favor certain classes of organic compounds while containing virtually none of others that form readily in laboratory simulations of interstellar chemistry. This suggests that the pathway from interstellar space to planetary surfaces acts as a filter, selecting for molecular stability and chemical robustness while eliminating more fragile compounds. Each meteorite fall represents a unique chemical experiment, a specific sample of the organic diversity that exists throughout the solar system and beyond. The continued study of these cosmic messengers provides an ongoing survey of extraterrestrial chemistry, revealing how the same fundamental processes that operate in interstellar space continue to synthesize organic compounds within the small worlds that populate planetary systems. They offer direct evidence that the chemical foundations of life extend far beyond Earth's biosphere, existing as a fundamental property of cosmic evolution itself. The most remarkable discovery in astrobiology may be that life's fundamental fragility masks an unexpected resilience, a capacity to endure conditions that would seem to preclude any biological activity whatsoever. In laboratories across the world, scientists subject microorganisms to the harsh realities of space travel. Vacuum pressures 1 trillion times lower than Earth's atmosphere, temperatures that approach absolute zero, and radiation doses that would prove lethal to complex life forms within minutes. Yet some organisms not only survive these trials, but emerge from them capable of resuming normal biological functions as if awakening from an extended sleep. The European Space Agency's expose experiments, mounted on the exterior of the International Space Station, have exposed bacterial spores, lichens, and other hardy organisms to the direct environment of space for months at a time. These biological samples experience the full spectrum of cosmic radiation, from ultraviolet photons that can shatter DNA molecules to high-energy cosmic ray particles that can penetrate several centimeters into solid matter. The temperature fluctuations range from over 100 degrees Celsius when facing the sun to minus 150 degrees in shadow. Thermal cycling that would fracture most materials within a few orbits. Bacillus subtilis, a common soil bacterium, forms endospores that can survive these extreme conditions for surprisingly long periods. When exposed to space vacuum, the spores dehydrate completely, their cellular machinery shutting down into a state of suspended animation that resembles death more than life. Yet when returned to Earth and provided with moisture and nutrients, a significant fraction resume metabolism and reproduction within hours. The spores achieve this remarkable feat through molecular mechanisms that essentially crystallize their genetic material and essential proteins, creating biological glass that maintains structural integrity across enormous temperature ranges. The survival strategies employed by these organisms reveal sophisticated adaptations that seem almost purposefully designed for interplanetary travel. DNA-binding proteins in spore-forming bacteria arrange themselves in geometric patterns that protect genetic material from radiation damage. Small acid-soluble proteins coat DNA molecules like molecular armor, preventing the formation of thymine dimers and other radiation-induced lesions that would normally prove fatal. Dipicolinic acid, a compound found almost exclusively in bacterial spores, chelates metal ions and helps maintain the crystalline structure that preserves cellular components during extreme dehydration. Tardigrades, microscopic animals commonly known as water bears, demonstrate even more remarkable resilience to space conditions. These 8-legged creatures, no larger than a grain of salt, can survive exposure to space vacuum for over 10 days while retaining the ability to reproduce successfully upon return to Earth. Their survival mechanism involves a process called cryptobiosis, where metabolic activity essentially stops and cellular water content drops to less than 1% of normal levels. In this state, tardigrades can survive temperatures approaching absolute zero and radiation doses hundreds of times higher than those that would kill most complex organisms. The molecular basis of tardigrade survival involves unique proteins called tardigrade-specific intrinsically disordered proteins, or TDPs, that appear nowhere else in the natural world. These proteins form protective networks around cellular components during dehydration, creating a biological matrix that maintains structural integrity even when normal cellular organization breaks down completely. When water becomes available again, the TDP networks dissolve, allowing normal cellular processes to resume with remarkable fidelity. Recent experiments have pushed the boundaries of biological survival even further, exposing microorganisms to conditions that exceed those found in most regions of space. Researchers have subjected bacterial spores to pressure levels found in the cores of giant planets, temperatures that exist near stellar surfaces, and radiation doses equivalent to those experienced during close approaches to Jupiter or passages through the Van Allen radiation belts. Some organisms continue to show measurable survival rates, even under these extreme conditions, suggesting that the envelope of biological possibility extends far beyond the relatively benign environment of Earth's surface. The time dimension of biological survival in space presents perhaps the most intriguing aspect of these studies. While most experiments expose organisms to space conditions for periods ranging from days to months, theoretical calculations suggest that some life forms might survive interplanetary journeys lasting millions of years. Bacterial spores embedded within meteorite-sized rocks could remain viable during the lengthy orbital migrations that occasionally transport material between planets, protected from the most damaging aspects of space exposure by meters of solid stone. Laboratory simulations of these longer duration exposures use accelerated aging techniques to estimate survival rates over geological timescales. By subjecting spores to elevated levels of background radiation or cycling temperatures at frequencies that compress millions of years into laboratory timeframes, researchers can model the degradation processes that would occur during extended space travel. The results suggest that while survival rates decrease exponentially with time, the mathematical tail of the survival curve extends surprisingly far into deep time. The discovery of extremophile organisms in Earth's most inhospitable environments has expanded the catalogue of life forms that might survive interplanetary transfer, Hyperthermophiles living near deep-sea volcanic vents can tolerate temperatures above the boiling point of water, while psychrophiles thrive in Antarctic ice at temperatures that freeze most cellular processes. Halophiles flourish in salt concentrations that would dehydrate most organisms. And acidophiles inhabit environments with pH levels that would dissolve metal. Each of these extreme adaptations represents a survival strategy that might prove useful during the stresses of space travel. The radiation tolerance of some terrestrial organisms rivals that of the most sophisticated human technology. Deinococcus radiodurans, nicknamed Conan the bacterium, can survive radiation doses over 1,000 times higher than those that prove lethal to humans. This remarkable resilience results from multiple DNA repair mechanisms that can reconstruct completely shattered chromosomes from fragments, plus cellular antioxidant systems that neutralize the free radicals created by ionizing radiation. These bacteria essentially rebuild themselves from molecular debris, suggesting that biological systems might be far more robust than previously imagined. Survival in space also depends on protection from the solar wind, the stream of charged particles continuously emitted by the sun. These particles can penetrate deeply into biological tissues, causing cumulative damage that builds up over time. However, organisms embedded within meteoroids or other solid materials would receive substantial shielding from this particle bombardment. Even a few centimeters of rock provides protection equivalent to Earth's entire magnetic field, creating radiation-safe havens where biological passengers might survive journeys between planets. The question of whether these laboratory demonstrations of biological resilience translate to actual survival during interplanetary transport remains open, creating one of astrobiology's most compelling mysteries. Computer models of the trajectories followed by material ejected from planetary surfaces suggest that the journey times between neighboring worlds can vary enormously, from a few months for the most favorable orbital alignments to millions of years for more typical scenarios. The organisms most likely to survive these journeys would need to combine maximum radiation tolerance with the ability to remain viable during extended periods of dormancy. Recent discoveries of microorganisms in Earth's stratosphere, at altitudes where atmospheric density approaches that of space, provide additional evidence for biological survival in extreme environments. These high-altitude organisms experience intense ultraviolet radiation, extreme temperature variations, and atmospheric pressures less than 1% of sea level values, yet they maintain active metabolisms and show no signs of physiological stress, suggesting that the transition from atmospheric to space conditions might be less challenging for some life forms than previously thought. The implications of biological survival in space extend beyond the possibility of natural panspermia to include concerns about planetary protection during human space exploration. If terrestrial organisms can survive interplanetary journeys, then spacecraft traveling to other worlds inevitably carry biological stowaways that might establish themselves in extraterrestrial environments. The same resilience that makes natural panspermia possible also makes it difficult to ensure that robotic missions to Mars and other potentially habitable worlds remain sterile. These survival studies continue to reveal new mechanisms by which life adapts to extreme conditions, expanding our understanding of biology's fundamental limits. Each experiment that pushes organisms beyond their apparent breaking points and finds that some fraction survive serves as a reminder that life's persistence often exceeds scientific predictions. The boundary between possible and impossible biological survival continues to shift toward more extreme conditions, suggesting that the universe may offer more opportunities for biological transport than conservative estimates would suggest. 4 billion years ago, Earth's surface resembled a battlefield where giant asteroids and comets delivered impacts that could vaporize entire oceans and melt continents down to their bedrock foundations. This late heavy bombardment transformed the young planet into a cosmic launching pad, hurling fragments of Earth's crust into trajectories that would carry them throughout the solar system and beyond. Each massive impact created pressures and temperatures that could accelerate rocks to velocities exceeding the planet's escape velocity, turning Earth itself into an inadvertent spacecraft manufacturer, producing millions of biological arcs that carried whatever primitive life might have already taken hold in the planet's earliest environments. The physics of impact ejection operates with a violence that seems incompatible with biological survival. Yet, computer simulations reveal that the process can be surprisingly gentle to materials buried beneath the impact site. When a kilometre-wide asteroid strikes Earth's surface at typical cosmic velocities, it creates a shock wave that propagates downward into the crust at speeds exceeding the velocity of sound in rock. This shock wave reflects off density boundaries deep underground, returning toward the surface as a rarefaction wave that can accelerate buried materials to escape velocity without subjecting them to the extreme temperatures generated at the impact site itself. The mathematics of these ejection events suggest that Earth could have launched approximately 1 billion tons of surface material into interplanetary space during the late heavy bombardment, enough to seed every terrestrial planet in the solar system with samples of Earth's early geology and whatever primitive organisms it might have harboured. The largest impacts would have been capable of ejecting rocks from depths of several kilometres beneath the surface, exactly the subsurface environments where early life would have found refuge from the sterilising effects of ultraviolet radiation and smaller impact events. Laboratory experiments using high-velocity projectiles and sophisticated pressure measurement equipment have confirmed that rocks can survive the acceleration phases of impact ejection while experiencing peak pressures comparable to those found at the centre of Earth. The key lies in the duration of the shock event, which typically lasts only microseconds even for the largest impacts. During such brief intervals, even extreme pressures cannot propagate deeply enough into rock samples to disrupt their internal structure completely, leaving cores of unaltered material that could preserve whatever biological contents they contained. The trajectories followed by impact ejector depend sensitively on the angle and velocity of ejection, creating a complex celestial mechanics problem that has occupied planetary scientists for decades. Most ejected material follows elliptical orbits that eventually intersect Earth's surface again, typically within a few million years of ejection. However, a small fraction achieves trajectories that carry it to other planets, with Mars being the most frequent destination due to its proximity and orbital resonances with Earth's trajectory around the Sun. The Martian meteorite collection found in Antarctica provides direct evidence that this interplanetary exchange has operated throughout solar system history. These rocks, identified by their distinctive mineralogy and trapped atmospheric gases that match the Martian atmosphere's composition, demonstrate that material regularly travels from Mars to Earth via impact ejection and subsequent gravitational capture. If this process operates in the Mars to Earth direction, it must also function in reverse, suggesting that Earth rocks have been arriving at Mars for billions of years. Some of these Martian meteorites show textural evidence for shock metamorphism that occurred during their violent ejection from the red planet's surface. Mineral grains display distinctive patterns of deformation that form only under the extreme pressure conditions generated by large impacts. Yet, the same rocks also contain unaltered materials that preserve their original crystalline structures through the entire ejection and transport process. This combination of extreme deformation and perfect preservation within the same sample demonstrates the heterogeneous nature of impact processes and their capacity to simultaneously destroy and protect different components of the same rock. The irony settles gently. The same cosmic violence that repeatedly sterilized Earth's surface also provided the mechanism by which any surviving life could escape to other worlds. Each catastrophic impact that reset the planet's biological evolution also launched rescue missions that could carry genetic information to safer environments beyond Earth's increasingly hostile surface. The late heavy bombardment thus functioned as both destroyer and preserver, eliminating local populations while simultaneously dispersing them across interplanetary distances. The survival of biological materials during impact ejection depends critically on their initial location within the target rock. Surface organisms would experience the full thermal pulse generated by the impact, with temperatures rising to thousands of degrees within seconds of the asteroid's arrival. However, microorganisms living in fractures and pore spaces several meters below the surface would be insulated from this initial heating, experiencing only the mechanical acceleration needed to achieve escape velocity. Recent computer models of impact ejection incorporate increasingly sophisticated representations of rock behavior under extreme conditions, revealing details about the ejection process that were invisible to earlier, simpler calculations. These models show that the largest impacts create multiple phases of ejection, with different materials achieving escape velocity at different times and from different depths. The earliest ejector comes from the immediate impact site and experiences the most extreme heating, while later ejector originates from greater depths and follows gentler acceleration profiles. The possibility that Earth's earliest life forms were already adapted to extreme conditions adds another layer of plausibility to impact-driven panspermia scenarios. If life originated in deep-sea hydrothermal vents or other high-pressure, high-temperature environments, it might have possessed the molecular machinery needed to survive the mechanical stresses of impact ejection. Hyperthermophile organisms that thrive at temperatures above the boiling point of water would find the brief heating associated with shock acceleration less challenging than organisms adapted to moderate surface conditions. The timing of Earth's transition from impact-dominated to biologically stable conditions creates a narrow window during which impact-driven panspermia would have been most effective. Before approximately 4 billion years ago, impacts were so frequent and energetic that they would have repeatedly sterilized the planet's surface, preventing the establishment of stable biological populations. After 3.5 billion years ago, impact rates had declined to levels that would rarely generate the escape velocities needed for interplanetary transport. The geological record from this crucial period remains fragmentary, with most rocks from the Hadean and early Archean eons having been destroyed by subsequent geological processes. However, the few surviving samples from this era show isotopic signatures consistent with biological activity, suggesting that life had indeed established itself on Earth by the time the late heavy bombardment was waning. These ancient biological signatures thus represent potential passengers that could have been launched toward other worlds during the final phases of intensive bombardment. The chemical composition of impact ejector would have included not only the rock matrix but also whatever water, atmospheric gases, and organic compounds were present at the impact site. Early Earth's atmosphere contained methane, ammonia, and other reduced compounds that could have provided additional protection for biological passengers during their journey through space. The combination of rock shielding and chemical reducing environment might have created surprisingly hospitable conditions for organisms adapted to anaerobic metabolism. The mystery deepens when scientists consider the possibility of return journeys, where Earth organisms ejected during the late heavy bombardment might have survived on other worlds long enough to evolve independently before returning to Earth via subsequent impact events. This scenario would predict that Earth's biosphere might contain immigrant populations that originated here, departed during the period of heavy bombardment, evolved separately on other worlds, and then returned to establish new lineages in Earth's later biosphere. The search for evidence of such biological round trips focuses on unusual organisms whose evolutionary histories seem disconnected from the rest of Earth's biosphere. Deep-branching microbial lineages that show little genetic similarity to other terrestrial life forms might represent populations that diverge during temporary residence on other worlds. Returning to Earth with molecular signatures of their extraterrestrial sojourn, however, the same genetic isolation could result from purely terrestrial evolution in extreme environments, making it difficult to distinguish between these competing explanations. As the late heavy bombardment gradually subsided, Earth's surface began the slow transition toward the more stable conditions that would eventually support complex ecosystems. Yet the legacy of this violent period continues to influence the planet's biology through the ongoing, albeit much reduced, exchange of material with other worlds. Every meteorite fall represents a continuation of the same process that once launched terrestrial life toward distant destinations, maintaining the possibility of biological exchange across the vast distances that separate the worlds of our solar system.